the Piezo SHOCK Show. We are on episode number 48, almost to episode 50. This is exciting. So what today we're going to speak about, I'm going to speak about what is the difference between clamping and damping of an ultrasonic transducer, and what might be an instance where you're clamping but not damping, and you might be damping but not clamping. And what's the difference? What might you want to do, and when would that be? So let's go. Let's go ahead and let this set. So let's just talk about why would you clamp an ultrasonic transducer. So clamping, I'll say it's basically attaching a structure to your transducer mechanically. So you expect maybe like you're putting it's bolted on, or it's pushed into something, which is mechanically kind of constraining a portion of it. That's what I would call clamping. Something that's mechanically constraining your transducer. And I see there's two reasons for that. One reason why you would want to clamp your transducer, I don't think I wrote that here, is also you will want to clamp because you want to damp it, because clamping can induce damping, but it's not necessarily the case. So let's talk about these two items before we get into damping itself. So the first is housing. Basically, you need a way to support your transducer, especially from my experience in ultrasonic surgical transducers, where you have the transducer inside of like a metal like kind of pen-shaped holder. Well, there is a specific kind of O-ring near the base of the horn, and this is very well known topic. So there's a O-ring at the base of the horn which kind of seals that portion, so it kind of squeezes into this pencil-shaped holder, which makes a really tight fit there. And then that's going to provide both an ability for the surgeon to hold the transducer from the casing, as well as protect it from any moisture that may creep in. There's also an O-ring in the back, which also seals it from the back. So one reason why you need to clamp your transducer or mechanically attach something to it as well, you need to hold it somehow. Even if you have a piezo buzzer inside of like a plastic housing, you have to hold that buzzer somehow. You have to put an O-ring or some type of epoxy to constrain it, to hold it. You can't just have it dangling off in free air. That's not much of a device, honestly. So you need to actually contain your device to be able to practically use it. And also, if you want to have some directionality to it, you would also in that case need to hold it. So that does make kind of sense. The other case is energy transfer. So this is also very true for non-destructive testing devices, where there's a transducer which can be mounted on your testing platform, whatever you're using. You're inspecting a pipe, you're inspecting a plate or something else, that you'll need to mechanically attach that transducer to your external environment. So in order to improve energy transfer, you need, or even just to establish it, you need to have mechanical coupling between your transducer and your environment in order to transfer the acoustic waves in, and then obviously receive them back as well. So those are the two reasons why you would why you want to clamp your transducer. And so why would we want to damp it? Damping means restraining its motion, with the intention. We have the intention here of restraining motion. We don't have the intention of holding it or putting it in a housing. Our intention is strictly to restrain the motion. Why would we want to restrain the motion of our device? Now, if you had clamped at a nodal point where there's not oscillation, that wouldn't be damping. There would be some minor effects of damping, but that wouldn't be really intentional. That would be kind of a side problem of damping, because you can never really get it perfect. Whenever you do attach something, there is an effect and a hit on the quality factor. No matter if you try to get exactly on the nodal point, this happens. It's real life. So why would we want to damp or reduce the oscillation? Didn't we always want higher oscillation? Let's take a look. So one reason that we want to damp our transducer is to increase the bandwidth, increase the operational range of our transducer, and make it more insensitive to frequency. This is really true for acoustic. So there's a couple of things here. One is for transient ultrasonic devices, where let's say you're sending a pulse several pulses and it's bouncing off some surface and then coming back. Well, the increasing the damping, adding specific like epoxy layers or other things that damp out the oscillation of your piezo is going to decrease the ring time, which is going to make the transducer better able to be a sensor. It can be used obviously also over larger frequency ranges. Also, if you do add damping to your transducer, that's typically what I'll see most. You really won't do that for ultrasonic transducers that are specifically actuators, unless your transducer itself becomes very difficult to handle in terms of its quality factor, in terms of the drive electronics. For some reason, you don't want a large change in your transducer's impedance once you have, like, let's say touchdown, let's say you're welding or something. It's typically not done, but I could see for a specific application, you might want to intentionally damp your transducer using some means of constraining or epoxy or something in order to reduce the quality factor to make it easier to control. But I primarily see damping as used in diagnostic style devices where sensing is and bandwidth is critical. And having a larger bandwidth, because as soon as you damp more, the quality factor reduces and the peak of the transducer spreads out. All right, so the other thing, why would you want to damp your transducer? Well, it's not exactly damping, but it's an indirect consequence of good mechanical coupling to your system. Let's say you had that non-destructive testing probe and you're mounting it to a plate. Well, now if you do have good coupling, you're going to significantly reduce the oscillation level, because now that oscillation is not going into your device. So hopefully that's not changing frequencies, and because that would be an improper design of the device, of your transducer. But let's hope that it's just damping and reducing the impedance, simply because now you have a path where energy is flowing and not resonating. It's just going into that substrate or medium. So it's an indirect consequence of mechanical coupling. And now here's an interesting one for ultrasonic transducer designers who are using their transducers more in an actuator sense, like welding or surgical or atomization, perhaps, in specific applications. This spurious mode suppression. Spurious mode suppression is one reason we would want to introduce damping. So what are spurious modes? If you've done an impedance analyzer sweep, you'll see spurious modes as, and I'm just going to draw it in thin air, where you have your impedance going down, and then you have all these little spikes, and you'll go back up and you get more spikes. And those spikes, those excessive spikes that happen around the resonance areas, are not actually the resonant mode you want to target. They're kind of byproducts of non-uniformities, of like, let's say, tolerances not being perfectly matched, of other things in their system resonating that don't produce useful output, but are linked closely to your resonant mode. So you want to reduce those modes. You want to reduce their appearance for two reasons. One is so you don't get energy going off in other places, and that energy going off in other places causes heat inefficiency and also can cause fracture for those specific areas of your device that are excited very strongly by those spurious modes. Secondly, it becomes very hard to control devices with spurious modes, because if you have frequency tracking, now all of a sudden your resonant device cannot, your algorithm cannot detect the actual resonant frequency, and you're not able to sustain a level of oscillation which is predictable. So spurious mode suppression. So one area of this is, let's give an example. Electrodes. Oftentimes we have electrodes. If let's say you have a piezo stack, and we have electrodes that we put in, not the ones that are printed on the piezos, the ones that are put in, and we have alternate polarity, and there's an electrode that can, copper or beryllium copper, that can wrap around, and that little part of the electrode that flares out, that can have a resonance. And oftentimes that resonance does end up being coupled closely, sometimes, not oftentimes, but sometimes it ends up being closely coupled to and closely related, at least in frequency, to your resonant mode. And that causes, you may hear ringing, but you will see impedance extra impedance spikes that can occur in your operation frequency range, for example. So you could redesign your electrodes, or what you could do is just, let's say you put some epoxy on that electrode to damp it out, to damp out that resonant mode. So now you've actually damped, well, not the main mode too much, but you actually have damped out the resonant mode of that electrode occurring. And wherever else you may find oscillation that isn't that you detect a spurious mode, either maybe perhaps in FEA you could predict what the spurious mode is, or you can just provide a kind of more general damping, because a lot of times spurious modes are high Q, because they only oscillate in a certain portion of your transducer. So that and that typically doesn't involve, sometimes it doesn't involve interfaces, but basically a small amount of damping can actually reduce the spurious modes. Maybe they don't make them disappear, but your algorithm will be a lot happier operating where the spurious modes are significantly damped, and you're allowing your main mode of resonance, your mode of high coupling, to continue to persist. A little bit of damping can go a long way in removing spurious modes. So are clamping, is damping and clamping, are clamping and damping different? Yes, they're different because it depends on your intention. So typically for ultrasonic, transducers uses an actuators to impart energy to the external world and not receive anything back, like welding, for example, or surgical or atomization. Clamping is used to hold your transducer. You're trying not to damp, but in some cases you can use clamping to damp as a byproduct. For example, non-destructive testing probes being put on the substrate. That's going to damp your transducer, but that's what you want. You want energy going into your system. You don't want it resonating in your transducer. There's no point to that. And so clamping and damping are different, but sometimes you can just you can clamp specifically to damp out those spurious modes. So they are different. They can coexist, but they're kind of different terms. Clamping is used in my most of my work. Clamping is supposed to be minimally effective, provides minimal changes to the transducer's behavior. You're trying to keep the quality factor and the natural mode of the system where it is. You're not trying to change those things. But in damping can be very useful if you do have a lot of spurious modes and you want to have a more pure response for your algorithm to work with. Now, what I will say is for damping, oftentimes when you do have your transducer by itself, it may have spurious modes, depending on your transducer, or definitely not for Langevin transducer. You don't want, or bolt clamp transducers, you don't want spurious modes at all. It's kind of not acceptable. But for other types that do have interfaces, epoxy joints that are quite critical, there's some bending going on, there's multiple modes occurring, you will find there are spurious modes and you may not be able to get rid of them. But when you do operate your device in its real environment at higher power, which by itself reduces the quality factor, and also as it's interacting with the environment, let's say you have an atomizer interacting with fluid, that load itself will provide damping. So it may not need to consider special circumstances in order to stabilize your transducer. That's why it's really useful to do high power characterization, high power impedance analysis with all of your loads and appropriate voltages and powers there. And as you may know, if you've been watching this series of videos, I do have a product that can help with that. It's called a closed loop transducer analyzer, and you can take a look at that from my website. So this ends our discussion, episode number 48, clamping versus damping for ultrasonic transducers. I'm going to put in the links, a link to the description, which is going to have a link to the presentation notes, as well as a link to my website, so you can check out my other consulting offerings on ultrasonic transducer development. If you're not already a subscriber for my email list, which you'll get updates from you can also scroll up through YouTube, but you can also do it through my email list, and then you'll get these presentation notes in your email, and you'll also just be kind of pretty up to date about what videos I'm producing. And yeah, feel free to reply to those emails or comment below. I'm going to get to your questions. All right, thank you for watching, and I'll see you next time on episode number 49.